Hey guys, welcome to our half-life example for logs and exponentials. So first off, what is half-life? Half-life is simply the amount of time it takes for half of some element or something to decay or go away. Typically, half-life is used in referring to carbon-based elements and things like that, or not carbon-based, but elements, specifically carbon. And so we use that in things like carbon dating and things like fossils. If you've ever heard, oh, this carbon dates back to so and so, that's using half-life ideas. So let's say that carbon 14, which is just a specific type of carbon, okay, has a half-life of 5,600 years. I believe that's somewhat accurate. We're going to do a few different problems. I want to first create an exponential function to model this. Then I want to figure out how much is left after, I don't know, say 12,000 years. And then I want to figure out after how long will there be so much. So let's say a sample initially has 60 grams of carbon 14. Okay, so these are the problems. So create an exponential model how much is left after 12,000 years, and how long until there's 10% left. So these are the problems. This is the statement. This is something similar to what you would see on a test as well. Okay, you would see our problem statement, which I may get a little more fun and creative with that, but ultimately this is the information you're being given. Create an exponential model after how much is left after this amount of time, and after how much time is this amount left. Okay, so let's do this. So to create an exponential model, we need 2 points. Well, I know it initially contained 60 grams. So that means I know we have 0, 60. I also know that it has a half-life of 5,600 years. So that means that after 5,600 years, I'm left with 30 grams. Now, before you guys jump and say, oh, that means that after, 1,120 years, or, yeah, 1,120 years, you'd have 0 left, right? Wrong. Now, from here, after another 5,600 years, we would have 15 grams, and so forth. Okay? So I can use this to create a function. And there's a few ways I can do this. Okay? First thing, no matter what, this is my initial value. So that means that the amount after t years, so anytime we're talking about amounts and time, a of t is a pretty common function, eh? It's going to have 60 as our initial value. Now, if you take in a chemistry class, you may know, be like, oh, there's a half-life formula, which is like 60 times 1/2 to the t over the half-life, and I don't want to do that. And you may be like, that's simpler, but it's a lot messier for the solving process that we're going to be dealing with, and this isn't that much more difficult. So what we're going to do is very simply say a to the t. Right? So this is exactly like creating an exponential function through 2 points given the y-intercept that we did in the exponential video. So all I need to do now is I substitute these in for our input and output and create an equation to solve for a. So that gives me 30 plus 60 a 5,600. From here, divide by 60. And 1/2 equals a to the 5600. So I take the 5600th root of both sides, okay, or raise it to the 1 over 5600. And we get a equals, get my calculator. So we have 1/2 raised, get this in focus on here, there we go. And then we just hit enter. 0.999876231 Now, when I'm going to write this down, I'm just going to write 99988. Okay? Some variation, right? We don't want to be like, oh, it's 1, because that's not right. So my final function, let's go down here. A of t equals 60 times 0.99988 to the t. Here's a really cool thing our calculators can do. They can store numbers. So like big crazy numbers like this, we can store it. And the way we do that is really easy. So we have that as our last answer. This one right here, this stow and an arrow. We want to press it. So this is saying take your last answer and store it as, we can store it as whatever we want. So we want to choose just one of the letters on here. So to get that, we can do alpha, and let's just store it as A. And then hit enter. So what's cool now is, what if I hit alpha and then A? I get that number. So in my calculator, A is now this number. That's cool. Now, why do I care? Well, that's part 1 of this problem. Part 2 said, how much is left after 1,200 years? So we're looking for A of 12,000 years? Yeah, 12,000 years. And that is 60.99988. Well, because we have A stored in our calculator, that whole thing, we can just do this all at once. It's really easy. So we can just do 60 times A raised to the 12,000. Hit enter. 13.59. So that tells me that after 12,000 years, there's 13.59 grams of this stuff left. Which, does that make sense? Does that work, right? We got to think about this too. Well, we know if we created a table, right, with time and amount, we started with 60. After 5,600 years, we had 30. After 11,200 years, we had 15. Okay. This is just shy, it's, 800 years shy of 12,000. And that was at 15, so if we go a few more years, we should go down a little bit more. So this makes sense. This works in the context of this problem. All right. Now, the last part of this problem, maybe the most challenging part. When do we have 10% left? After how long do we have 10% left? There's a couple things we have to do. First, we have to figure out, well, what's 10% of what we initially had? So we find what's 10% of 60. To do that, simply take 60 times 0.1 for 10%, and we get 6. That's it. I mean, I chose easy numbers, but it might be like, what's, 12, when did it have 15% of 78? Might not be as easy. So that means I need to solve, and I need to solve this. So divide by 60. 0.1, 0.9. Okay. What do I do? Oh, that's right. If the variable is in the exponent, logarithms. Logarithms. So the base of my logarithm is going to be this 0.99988. So it gives me log base 0.99988, which is really just the a value in our that we have stored in our calculator, right? And now the input and output flips. This because of 0.1 equals t. This right here is our exact solution. But if I tell you that, oh yeah, hey, it's going to take log base 0.99988 of 0.1 years for that to happen, you're going to look at me like, is that like 1 year? Is that like 1 billion years? What's happening? What is that? This is an example where we need to get an approximate solution to be able to understand what the heck is going on. To do that, we use the change of base formula. So t is equal to, and let's do natural log. We haven't done a lot with natural log, but it's the same, and we have a button on our calculator, so it's no worries. So the natural log of 0.1 divided by the natural log of 0.99988. Okay, so we go to our calculator. Okay, and we use the natural log of 0.1, close that parenthesis, divided by the natural log of a. Close that parenthesis. 18,602 years. So if it goes a little over, right, it's going to happen in that many years, or if you want to, you can round up. Okay, we'll just go with kind of the nearest year. 18,603 years. So it's going to take 18,603 years approximately until we have 6 grams left, or 10% of our original sample. And that's half-life. Hope you have fun with it. I'll see you later.